Well, let's continue. So now we do the check whether the amplification factor that we derived is between -1 and 1 because it's real. So under which condition is this satisfied? So we have here to check whether which conditions we have the G of, now we introduce here a new parameter for k delta x, whether that is between -1 and 1. So the beta that is also used for the book, that is the abbreviation of the wave number k times the grid spacing delta x. So in our case we have then -1 smaller equal, and the g that was 1 minus 4r, and then the sine squared. Now instead of k delta x we write the beta. That has to be small equal than 1. So we check now under which conditions this is satisfied. So the right hand side is easy because the sine squared is always greater or equal to 0, and so we need the r to be positive. So that means this inequality is okay for r greater or equal to 0. The left inequality we can write in a different way. We can put this on the left hand side, so then this is equivalent, the left hand side, to seeing 4r sine squared beta half is smaller or equal than 2. So we order a little bit. And now we make a trick. We say, we observe that we can estimate the sine squared up by 1. So that means we have the relation that the 4 sine squared of beta half is smaller or equal than 4r, because the sine squared is at most 1. And then we do the following: we require this to be smaller or equal than 2. If we have this satisfied, then this inequality will hold, and then this, and then this. So that means if we choose r in this way, we get the left inequality. So, and this is satisfied for, this is equivalent to saying that r has to be smaller or equal than 1/2. So that means the left inequality is satisfied when we have this. So that this left inequality satisfied for r smaller or equal to 1/2. The right inequality for r greater than 0. Then we have our stability condition. So from that we get then the stability condition of the forward time centered space scheme. That is then, as we derive now, the condition that the stability parameter r has to be between 0 and 1/2. And the r is alpha delta t divided by delta x squared. And this is sometimes called, it is not so common actually, but I think John von Neumann would deserve this. He was the one who came up with this stability analysis that has his name, von Neumann stability analysis. So there is the condition that we have been using in the computations and that you continue to use also in exercise 5. And there you will actually do this, what we did here, go through it yourself, and then you make sure that you understand this really well. If you have any questions, just ask me or one of Jürgen, Alexander, or Reda during the exercises sessions. So, then we have now established consistency, that was yesterday, of the FTCS scheme, and now under this condition here we have also stability. So that means the solution and also the rounding errors stay bounded as we go to n towards infinity. That is stability. And consistency was that the PDE is approximated by the finite difference method as we refine the grid spacing delta x and the time step delta t. But what we want is that our numerical solution, ujn, that approximates the exact solution of the PDE. And that is what we call convergence. So that is the third key concept in the numerical analysis of finite difference methods. Consistency, stability, and convergence. Definition, now I can give that quite concrete. Finite difference method of the partial differential equation is called convergent if the finite difference method solution that we note here by this boldface UN converges to the exact solution that we usually denote by U of x, and now it is at Tn of the PDE. And that can also be expressed in the following way. That means if for a time t between 0 and say some maximum time that we want to compute, that within this time interval that we are interested in, following holds, that the limit of delta x and delta t approaching 0, and now we take again as we did for the I think we had it already for the consistency and the stability, the true norm, and now we indicate the time level in this way, the t divided by, so this is then again the boldface U here, the numerical solution, vector, and the t over delta t is then the n. So we prefer this because then we then always are going to the right time. When we refine the grid, then we have to do more time levels. So by that expression we get this what we want. Minus the exact solution, and now we write this with a point because we are using here a norm, and I explain it in a minute. The 2 norm that we had already discussed earlier, that has to be equal to 0. So that is what it's saying. So that the numerical solution, this one, is approaching the exact. Now let me write what this means, because the point looks a little bit strange, but it's just indicating that we are taking this norm then at the grid points. So we have then here the norm of U of this numerical solution, and here we have the U of the point T, 2 norm, that is equal to two norm, we have always the grid spacing, delta x, times the sum, in our case it is from J1 to Nj, and then we take the numerical solution at the grid point J at the time level t over delta t. So this is some n here, minus the exact solution, and that is now what the point means. Then we take that at the grid points. We are considering the time t, and then we take that squared, and after having taken the sum of this difference multiplied by delta x, we take the square root. So that is then the true norm. So that is what we mean by the numerical solution approximating the exact solution. So that is what we require. That is really our goal. That the numerical solution that we compute approximates the exact solution. We can do that in this sense. This is usually not so easy to do, to show convergence. But there we have good help by Peter Lex, and we are using his Lex equivalence theorem. I showed you a picture of him in the beginning. So that's the one who got the Abel Prize a few years ago. And it says the following: a consistent finite difference method. So then we have, now we get all the terms that we learned. Consistent finite difference method for a well-posed linear initial value problem. So that is a PDE where we just have initial values involved, so no boundary conditions, but we may have periodic boundary conditions. That is no problem. That is convergent if and only if it is stable. So let's digest that. So consistent finite difference method for well-posed, that means that a solution exists, is unique and depends continuously on the data, in that case on the initial condition. So consistent finite difference method for a well-posed linear initial value problem. So that is also important. For nonlinear we cannot say so much, but for linear we can. If that is convergent, it is convergent if and only if it is stable. So that means what we have to do is we have to show that the finite difference method is convergent, so is consistent, and then convergence and stability are equivalent. So that is the theorem, and it says now briefly, for a consistent finite difference method, convergence is equivalent to stability. So that is the way we can summarize the Lex equivalence theorem. What that means for practical applications is that we first show that the finite difference method is consistent, and then that we show that it's stable, and then we know it is convergent. Okay, so let us do that for the forward time-centered space scheme. So look now for the convergence of the FTCS scheme. Consistency, that was shown. We have a more elaborate consistency analysis in 23. Here we had the leading order terms, and when we just have the basic order was 24. Stability, that we have just shown a minute ago. Shown for periodic boundary conditions. That is always what we do here, because we can only do that we can only have periodic boundary conditions for the phenomenon stability analysis. But we see that it's boundary conditions. If the stability parameter R is between 0 and 1/2. And then we can conclude, we can follow from this Black's equivalence theorem that then under this condition, for periodic boundary conditions, the finite difference method is also convergent. So follows with the Black's equivalence theorem that the FTCS is convergent for periodic boundary conditions. Can be even take it as it is, if and only if the R is in between 0 and 1/2. And again, remind us what the R was. The R is, in our case, the thermal diffusivity times the time step divided by the grid spacing squared. So then we know when we respect this stability limit, and we use the FTCS with periodic boundary conditions, then we are sure that the numerical solution will converge towards the exact solution. And that is what we want. So I have stressed a little bit here the periodic boundary conditions, and that is for good reason, because it's only valid for that. But it turns out that this is also a necessary condition for stability when we do not have periodic boundary conditions. When we have directly boundary conditions giving values the boundaries that what mostly we have been doing, and Radar showed also one example. It was a flow in a channel when we had a derivative, the condition that is a non-boundary condition. If we have these cases, then the stability condition for periodic boundary conditions is a necessary condition. So if that is not fulfilled, then we can forget about it. So, but this gives us now the confidence in using this method, because we know that the solution, numerical solution, will really approximate the exact solution as we define the grid spacing and the time step. So now we want to see how we can apply this theory, this numerical analysis, also to other situations. We shall take the implicit finite difference method. It's called the simple implicit method in the book that we already saw. We take that as an example. And then you can see that we can speed up a little bit of the analysis. We don't to go through everything again, but it's good to have an understanding of what it is all about. So then we do a numerical analysis. now of what is called in the book the simple implicit method. And that is what we have also seen, has been also named after the scientist who devised that first Larsemann, and that was what we looked at in 13. And the method, just to remind you, is the following. We have the discretization of the time derivative in the usual way. New time level minus the one at the old time level divided by the time step, which approximate the du dt. And on the right hand side, we have the discretization of alpha times the second derivative of u with respect to x. And the difference between the forward time center space speed is now only the time level. Here we have now the new time level. Otherwise, it's just the same as the forward time centered scale, the centered space. Now we do the analysis, and we start with consistency. So what is the recipe? The recipe is insert the exact solution of the PDE, that is u of xj tn for ujn into the finite difference method, which is 39, to get the truncation error. That is 40. And the truncation error, we noted that xtn at xjtn, gridpoint xj time level tn, taking the grid spacing delta x and the time step delta t. And I stress again, when you do the consistency analysis, it is important that you get it in this form. Or even better, we take this on the left-hand side, and then we have this minus this is equal to 0. It is always important for the consistency analysis that you see the approximation of the first time derivative. So we insert it in there, and then we get u of x j tn plus 1 minus u of x j tn divided by delta t. So that is what we also did for the forward time centered space. And now we take the minus, so we take it to the minus on the left hand side, alpha divided by delta x squared, and we insert now also here the exact solution at the right grid points and the right time level. That is the grid point in that case xj plus 1 and the time level tn plus 1 minus 2 times grid point xj and time level tn plus 1. Then the u of xj minus 1 time level tn plus 1. And that is it. So, then we have to compute that. And that is, I stressed also that, not 0. Because we are now not doing approximations, we have now the exact solution, and for that we get actually something. And that is what we want to compute. That is the truncation error. Now we do a little trick here, but we can understand this trick quite easily when we just watch this truncation error for just a short while, because we observe that all on the right-hand side is at the new time level. This is also at the new time level. So in this case, it makes sense to make the Taylor expansions around the new time level. So that is a trick. So easier to do Taylor expansions or Taylor expansion around well, the x, that's like t equal to t n plus 1. Then tn. And we also do it around xj as usual. So that means that we take then x u of x tn, and that is then equal to u of x tn plus 1 minus delta t. So then we do the Taylor expansion around that. So then we do it as u, and then we have it here that we get a minus delta t ut, and then we get plus order. Here we are not so ambitious as we were before, because we cannot play the trick there with the special r when the forward time center space is very accurate. So here it means the u and so on means the u of xt, and the x is xj, and the t is tn plus 1. That is what we are using here. And the Taylor expansion around for xj plus and minus 1 is the same as we did before, but it is then taken at around this tn plus 1. So that is standard. And if we do that, then the truncation error becomes the following. We have now, this is now our u, right? The u of xj tn plus 1. So that is now our u. And the u at xj tn, that is now this, that we take the Taylor expansion. So then that is u minus delta t ut plus order delta t squared divided by delta t. And then we have the minus alpha over delta x squared. And then here we have the usual expansion, and I just write it. It is the same as for forward time center space, but it is taken at the new time level. But this doesn't make any difference because we are doing the expansion in x. So we get then the u plus delta x ux plus delta x squared half uxx, and delta x to the power 3 divided by 6, third derivative, and also here we don't need to be more ambitious than that. That is the u of xj plus 1 tn plus 1, because we are now developing around xj tn plus 1 everything. Then we have the minus 2u, that is just as we have it there. There is no change to that. That is already at the right location. And now we do Taylor expansion for u of xj minus 1. So that is then getting us here a minus. Here the minus delta x squared gets plus delta x squared. And here we get a minus delta x to the power 3 is minus delta x to the power 3 divided by 6, u third derivative, and also the fourth order term. And that's it. And now we can observe again that most vanishes, and we are left then following. see that the truncation error is equal to, let us go through. The u cancels, delta t can be factorized. The u plus u is plus 2u, minus 2u is 0. The plus delta x ux and the minus delta x ux cancel. The same is true for the third derivatives. And we are only left with 2 times this. So this gives delta x squared times ux, x. And with this delta x squared, we just get the uxx. And here we get order delta x to the power 4. And with this, we cancel delta x squared. This gives delta x to the power 2. So what we get in the end is ut plus order delta t minus alpha uxx plus order delta x to the power 2. And now we see here the PDE, but there we observe that we have inserted the exact solution of the PDE. And that means the exact solution for the PDE, then this is 0. So that is PDE is 0 for the exact solution. Therefore, we can get in the form that we finally use that what is remaining is first order in time and second order in space. So that means that the simple implicit method is first order in time, second order in space. And that's the same as for the time-centered space. So in that respect, the methods are equivalent. So first order accurate in time, and second order accurate in space. So then, but from this, the important thing is when we have this, the truncation error will go to 0 as we refine. So that means the limit delta x delta t to 0 of the truncation error is 0. And that means that the method that we considered here, so the simple implicit method is consistent. So then we have established that. And then the next step is stability. If we want to know a little bit more than how the error terms look like, we would have to take more terms in the expansion as we did for the time-centered space, but we skip that here. Instead, we look now at stability. First, we write the equation in a form that is more suited for doing the stability analysis. Remember the consistency analysis, you must see the time derivative discretization when you write it. But here it is more advisable to put everything unknown on the left and everything known on the right. We can do that in the following way. So we put everything that we know on the left, and that was, if we think of it, we get 1 plus 2r uj, and I think we have already seen that. We discussed this method in the context of the method of lines. So we can write them in this form: uj plus 1 n plus 1 plus uj minus 1 n plus 1. That is equal to the ujn. So then we have everything unknown on the left, everything known on the right, and r is again our stability parameter. Now we insert a Fourier mode for ujn. So you see, we'll do that now much more quickly than before, because we know what we are doing. And we understand the context. It was important to give you the context, therefore it was a little bit elaborate for the time-centered scale. But now we do just this. We insert this node for ujn into the form 42. And that we give a name. We gave this 43. We gave this name here for the Fourier mode. So then we do that. What do we get? First, we observe that everywhere here, for the n plus 1, we will get the Fourier mode at the new time level. Here, here, and here. So we can factorize that. Then we get 1 plus 2r. And then we get, well, we can write it everything equally. Let's see. I make the steps, I do the factorization later. So we put in this here. So we get then the u hat n plus 1 for wave number k e to the I k x j minus r u hat n plus 1 for wave number k, and the xj that will get this here e to the I k x j plus 1. Then we get here a plus u k hat n plus 1 e to the I k x j minus 1. So then we have the left hand side. On the right hand side we have just the u k hat, the Fourier mode for wave number k at the old time level times e to the I k x j. And now we can factorize what I already tried to do earlier, but now we can do it really. You'll see it. The UK and this one on the left side, and we can also divide the whole equation by e to the I k x j. So divide by e1 to e to the I k x j. Let's see, no. Yeah, it was right. So we divide by, you can also do it and divide e to the I k x j, the whole equation. And we factorize. So then we get here 1 plus 2r. That is factorized, that is vanished because it is divided by, and here we get minus r. This is factorized. If we divide by e to the I k x j, we get from that part e to the I k delta x. Remember, this is xj plus delta x, and then we can do it in this way. And here we get the similar thing with a minus. So then here we get minus e to the minus I k delta x. So then we close the bracket to write the Fourier mode at the new time level that we have factorized. and we have here an error, which is a plus. So this is a plus, because this is a plus. And on the right-hand side, we simply have, after dividing by this, just the Fourier mode u, k, hat, n. That is the Fourier mode for wave number k at O time level. And from that, we see immediately what the factorization, amplification factor is. Amplification factor is this divided by this. So we have to divide by this square bracket to see the amplification factor. So then amplification factor is g of k delta x, that is u hat, the Fourier coefficient at the new time level divided by the old time level. In our case, it means that we have, as I said, divide by this square bracket, that is k plus 1 equal to that, then we divide by that, and then we see that we get the following. We get that the amplification factor in that case is 1 divided by 1 plus 2r, and then we get minus r times these terms that we have there, e to the I k delta x plus e to the minus I k delta x. Now we can again use Euler's formula to see that this is cosine plus sine, this is cosine minus sine of these arguments k delta x, so 2 cosine. So this would be 2 cosine of k delta x using Euler's formula. And then we see that we get 2r minus 2r, something times cosine. So let us write that. So we get then 1 divided by 1 plus 2r. Then we can factorize that because we have the 2r here, and here we'll have the minus 2r. So that we get here the minus cosine of k delta x. And for this 1 minus cosine, we can again write by trigonometric formula that this is equal to 1 plus 4r sine squared of k delta x half. So then we have it in this form. And that is then what we shall use. So here we use the formula that 1 minus cosine, if I write it with beta, that is equal to 2 sine of beta half. So that is what we do. So then we can apply the stability condition. We just give it a number. 44 for the amplification factor. And up a little bit. But we can easily see now that the stability condition is satisfied. That is that the amplification factor g of k delta x has to be small or equal than 1. In our case, that means that g of k delta x is in our case 1 over 1 plus 4 sine squared of k delta x half. And that is clearly smaller equal than 1 for r greater equal than 0. And that means that the method is unconditionally stable. So from that we see that the simple implicit method is unconditionally stable. That means we can choose any time step regarding stability. That does not mean accuracy. Unconditionally stable. And by Lex equivalence theorem, then this method is convergent. It is convergent for any r greater equal than 0. So then we are finished. So then we have established what we want. The simple implicit method converges for any stability parameter r greater equal 0. Okay, so then we are finished here. You can read more about that, also other methods that I did not explain you, like the Crank-Nicolson method or others in the book. But next week we will start with the linear advection equation. So that will be, then the next 2 weeks will be devoted to hyperbolic problems.